Okay, I want to talk about the correct way to write a weak acid, strong base neutralization reaction. I'm going to represent the weak acid, first of all, just generically as HA. Then I'll get into some examples where it's not quite that simple looking. I'm going to represent the weak acid as not dissociated. The difference between a weak acid and a strong acid is that a strong acid would break apart into H plus and the anion, but a weak acid only does that to a small extent. It's only very partially ionized, so it mostly stays together, so I'm representing the weak acid as HA. I'm going to react it with a strong base. By definition, a strong base is a soluble hydroxide. So it's probably an alkali metal or alkaline earth metal hydroxide. That metal is a spectator. So I'm not going to include the metal in my net ionic equation. I'm just focused on the hydroxide, which is actually doing something the metal is not. I'm going to represent this reaction with a straight arrow. Neutralization reactions always have very high K values, so we can assume they go to completion. The hydroxide is going to pull an H plus off of the weak acid, giving us the conjugate base. The conjugate base here is A minus. The conjugate base is always going to be the same as the structure of the weak acid, but without an H plus. So you have to lose the H, and you also have to lose a +1 charge. The hydroxide pulled the H plus off of the HA and left us with the conjugate base and water. So this is kind of generically what these things are going to look like. But let's take a look at a couple of them that don't quite look the same, but if you look closely, the pattern's the exact same. What if my weak acid is something like the ammonium cation? This thing's not neutral like HA. It has a +1 charge, but it's still a weak acid. If I react it with a strong base, it still goes to completion, and the hydroxide is still pulling an H plus off of ammonium. That's going to leave us with ammonia. Ammonia is the conjugate base of the ammonium cation. It is a weak base, and I get a water molecule. Okay, what if I have a weak acid that looks like this? Hydrogen phosphate. You've probably heard me use the term amphoteric. It means that in some sense it can act as an acid, in some sense it can act as a base. Hydrogen phosphate is the conjugate base of dihydrogen phosphate, which is the conjugate base of phosphoric acid, H3PO4. So this last H is the last H to come off of phosphoric acid. If I react it with hydroxide, it's going to follow the same patterns as the one above. The hydroxide is going to pull that last H plus off of the hydrogen phosphate. That's going to leave me with phosphoric acid and a water molecule. Okay, so let's look at how all of these balanced equations are balanced, both as to mass and charge. Being balanced as to mass is exactly what you think being balanced means. Starting up here at the top, I've got 2 hydrogens on the left, 2 hydrogens on the right, an A on the left, an A on the right, an O on the left, and O on the right. That's balanced as to mass. But look at the charges. HA is neutral. It does not have a charge. Charge is 0. Hydroxide is -1. So the entire reactant side of this thing has a net charge, a total charge of -1. Look at the right. -1 for the A minus, neutral for the water. The right-hand side has a -1 charge. So it is also balanced as to charge. Coming down here to the second reaction, +1 for ammonium, -1 for hydroxide. Total charge on the left, 0. 0, 0 for the products. Total charge on the product side, 0. And then down here, the hydrogen phosphate, -2, hydroxide, -1. So a total charge on the left of -3, The phosphate is -3. The water's neutral. Total charge on the right, -3. The charges must balance for the equation to be balanced. If they don't, it's not balanced. Also, one more thing to point out. Notice that the conjugate bases always have a charge that is one lower than the weak acid they came from. So if I have a weak acid that is neutral, charge of 0, like HA, my conjugate base has a -1 charge. If I have a weak acid that has a +1 charge, like ammonium, the conjugate base is neutral, 1 less than +1, 0. And if I have a weak acid that has a negative charge, like this hydrogen phosphate is -2, the weak base is even more negative. Phosphate is -3, 1 less than -2. Okay, I hope this helped with writing weak acid, strong base, net ionic equations.